Lecture 1.5, Functions and Logarithms. This photo is the Golden Gate Bridge in San Francisco, California, taken by Vicki Kelly in 2004. And if you'll notice, down below the bridge is Fort Point, a pre-Civil War era fort built of red brick to protect the Golden Gate. A relation is a function if, for each x, there is one and only one y. A relation is 1 to 1 if also, for each y, there is one and only one x. In other words, a function is 1 to 1 on domain D if f of a cannot equal f of b whenever a cannot equal b. To be 1 to 1, a function must pass the horizontal line test as well as the vertical line test. For example, y equals 1/2 x cubed passes the horizontal line test because there is no place you can draw a horizontal line and hit the function more than once. So it is 1 to 1. The function y equals 1/2 x squared, which we recognize as a parabola, is not 1 to 1 because we can draw a horizontal line and hit the function twice. This horizontal parabola, x equals y squared, fails the vertical line test, so it's not a function. And it's also not 1 to 1. Inverse functions. F of x equals 1/2 x plus 1. We recognize as a linear function. We can write it y equals 1/2 x plus 1. Given an x value, we can find a y value. We solve for x, subtracting 1 from both sides, multiplying both sides by 2, and then moving the x out front. We then switch x and y, getting a new function, y equals 2x minus 2, which we write f inverse of x equals 2x minus 2. If we graph the inverse function, what we notice is that it's a reflection about the line y equals x. This is true for all inverse functions. Example 3. This is example 3 from some calculus book I used sometime in the distant past. F of x equals x squared, where x is greater than or equal to 0. So we want to graph f of x, f inverse of x, and y equals x for x greater than or equal to 0. We can do this parametrically on the TI-89. We press diamond, y equals, and for the original function, we enter x1 equals t, y1 equals t squared, and t is greater than or equal to 0. For the inverse function, we enter x2 equals t squared, y2 equals t. And for the line, we enter y equals x as x3 equals t, y3 equals t. Then we press diamond window and set up an appropriate viewing window. When we press diamond graph, we see our two curves and the line of symmetry. Find the inverse function. We start with y equals x squared, where x is greater than or equal to 0. Solve for x by taking the square root of both sides. So we get x equals radical y. We switch x and y, giving us y equals radical x, or f inverse of x equals radical x. We change the graphing mode to function. Diamond y equals y1 equals x squared such that x is greater than or equal to 0. Greater than or equal to is diamond greater than. y2 equals radical x. y3 equals x. And we press diamond window, set up an appropriate viewing window, and press diamond graph. Once again, we have the original function and its inverse. Consider f of x equals a to the x. This is a one-to-one function, therefore it has an inverse. The inverse is called a logarithm function. Example, 16 equals 2 to the 4th. So 4 equals log base 2 of 16. 4 is an answer to the question, 2 raised to what power is 16? The most commonly used bases for logs are 10, as in log base 10 of x, which we write log x, and e. Log base e of x is normally written ln of x. Y equals ln x is called the natural log function. Y equals log x is called the common log function. In calculus, we will use natural logs exclusively. We have to use natural logs. Common logs will not work. A few historical notes. Logarithms were invented by a Scottish nobleman named John Napier, who lived from 1550 to 1617. Logarithm is the combination of two Greek roots, logos, which means reason or ratio, plus artemis, which means number. The word logarithm was introduced in Napier's 1614 work, Mirifici Logarithmorum Canonis Descriptio, Description of the Wonderful Canon of Logarithms, originally published in Latin. Here's the first English translation by Edward Wright. Astronomer Johannes Kepler read Napier's work in 1616 and used logarithms in developing his third law of planetary motion. Kepler's third law states the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. Kepler published the third law in 1620 in a book titled Ephemerides, dedicated to Napier. He later published his own work on logarithms. The term natural logarithm, actually logarithm ephemerides us naturalis, was first used by an Italian mathematician, Pietro Mengoli, who lived from 1626 to 1686. Surprisingly, the notion ln for natural logs was not first used until 1893 by an American, Washington Irving Stringham, who lived from 1847 to 1909. In place of E-log, we shall henceforth use the shorter symbol ln, made up of the initial letters of logarithm and of natural or Naperian. Even though we will be using natural logs in calculus, you may still need to find logs with other bases occasionally. Here's a useful keyboard shortcut for the newer TI-89 titanium calculators. Unfortunately, the shortcut does not work on the older TI-89s. Diamond 7 returns log. If you enter log 1000, you get 3, which was the common log in base 10. If you enter log 32.2, you get 5, which is the base 2 log. And while we're on the topic of TI-89 titanium keyboard shortcuts, pressing Diamond 9 returns root. If you enter root 32.5, you get 2, which is the 5th root. For a quick key to all of the TI-89 titanium shortcuts, press Diamond EE, which says key above it, and you get the key to the shortcuts. Here are some properties of logarithms. A to the log A of x equals x, log A of a to the x equals x, where a is greater than 0, a is not equal to 1, and x is greater than 0. Since logs and exponentiation are inverse functions, they undo each other. The product rule, log a of xy equals log ax plus log ay. The quotient rule, log a x over y equals log a x minus log ay. And the power rule, log a x to the y equals y log a x. And the change of base formula, log a x equals ln x over ln a. These rules are still useful, but they were even more useful in the days before computers and calculators, because they could change the more difficult function of multiplication to a simpler function of addition, and more importantly, they could change exponentiation to multiplication. It also allowed us to find fractional exponents. If $1,000 is invested at 5.25% interest compounded annually, how long will it take to reach $2,500? We have 1,000 times 1.0525 to the t equals 2,500. Dividing both sides by 1,000, 1.0525 to the t equals 2.5. We use logs when we have an unknown exponent. Taking the log of both sides, and you could have used common log, but since we're in calculus now, we're going to use the natural log. We can move the exponent out front and solve for t. Now we use our calculator to get an approximate answer, 17.9. So about 17.9 years. In real life, you would have to wait 18 years.